Triangles, triangles, triangles. This activity goes over the rules and processes for figuring out angles and lengths of sides of right triangles and non-right triangles. For non-right triangles, we will use law of sines and law of cosines. For the right triangles, we will use our definitions of our 6 trig functions and Pythagorean theorem. This screen is a reminder of the definition of sine. In a right triangle, sine of an angle is equal to the ratio of the length of the opposite side to the hypotenuse. This screen is a reminder of the definition of cosine. In a right triangle, cosine of an angle is equal to the ratio of the adjacent side to the angle divided by the length of the hypotenuse. Here we have a reminder of the definition of tangent. In a right triangle, the tangent of an angle is equal to the ratio of the length of the opposite side divided by the length of the adjacent side. Here we're reminding about the other 3 reciprocal functions. Cosecant is the reciprocal of sine, and so in a right triangle, cosecant of an angle is equal to the length of the hypotenuse divided by the opposite side. Secant is the reciprocal of cosine, and so in a right triangle, secant is equal to the ratio of the hypotenuse length divided by the adjacent side. And cotangent is the reciprocal of tangent, and so in a right triangle, cotangent of an angle is equivalent to the adjacent side divided by the length of the opposite side. Here we have an example for a right triangle. We have a person hitting a volleyball 20 feet away from the net, and the net is 4.5 feet high above where they're hitting the ball. We want to find the angle at which Jan will have to hit the ball. So we are going to use tangent because we have the opposite side of 4.5 feet and the adjacent side of 20 feet. So tangent of theta will equal the ratio of 4.5 over 20 feet. Since we want to find the angle, we are going to need to use the inverse tangent function. So inverse tangent or arctangent of the ratio 4.5 over 20 gives us an angle of 12.68 degrees. Jan would have to hit the ball at an angle of 12.68 degrees to get it over the net. We have another right triangle situation here. We have a little girl trying to hit a piñata, and the piñata is 10 feet above the ground. There's a tether 7.5 feet from where the piñata is pinned. We want to find the angle that the tether is making with the ground, and we also want to find the length of the tether. So we'll use Pythagorean theorem to find the length of the tether, and we will use inverse tangent to find the angle. Using Pythagorean theorem, the length of the tether will be the square root of 10 squared, because 10's one of the sides of the right triangle, plus 7.5 squared. 7.5 is the other perpendicular side of the right triangle. If I take the square root of 100 plus 7.5 squared, I will get approximately 12.5 feet as the length of the tether. And then the angle will be the inverse tangent of the opposite side of 10 divided by 7.5. So inverse tangent of 10 divided by 7.5 is 53.13 degrees. Here we have a situation again involving a right triangle. We have a building being built, and we need a 150-foot clearance from the building to the road. We're given a surveying measurement of 41 degrees, 17 minutes, 15 seconds from north, measured in the westerly direction. Then we have a length of 200 feet as the hypotenuse of a right triangle. The angle that we need is actually the complement of that measured angle. So first we're going to need to take 90 degrees and subtract the 41 degrees, 17 minutes, and 15 seconds. And then once we have that angle, we can use sine, which involves the opposite side and the hypotenuse, to figure out the length d, which will tell us if we have enough clearance. In order to correctly subtract that measured angle from 90 degrees, we want to turn it into its decimal degree form. Remember from earlier in the semester, 17 minutes should be divided by 60 because there are 60 minutes in a degree. And then 15 seconds should be divided by 3,600 because there are 3,600 seconds in a degree. So 41 degrees, 17 minutes, 15 seconds is equivalent to a decimal degree of 41.2875. So subtracting that measured angle from 90, we get 48.7125 degrees. Now that's the angle that's inside of our right triangle. Sine's definition in a right triangle is it's the ratio of the opposite side to the length of the hypotenuse. So sine of 48.7125 will be equal to the length D divided by 200. Solving for D, I multiply both sides by that denominator, and I get 200 times sine of 48.7125 degrees, and that gives me 150.28 feet. There's just enough clearance. Another nice application of right triangles involves reading a contour map. Here we have a very simplified contour map in which the distance in elevation between each ring is 175 meters. So every time you jump from ring to ring, it means you're going up or down by 175 meters. On this particular map, if you measured with a ruler 1 centimeter, it would be equivalent to 400 meters in real life. On this map, we're going to suppose that when we measured with a ruler from point A to point B, it was 2.5 centimeters. We're interested in figuring out the angle of inclination of the hill and how far it would be if somebody went up the slant of the hill from point A to B. We're assuming that it's kind of a smooth hill and not one that has dips. So on our contour map, there were 4 rings between points A and B. So every ring is an increase of 175 meters. So from A to B, 175 times 4 equals a 700 meter gain in elevation. That's the opposite side of the angle of inclination. If we measure 2.5 centimeters on the map, every centimeter is 400 meters in real life. So 2.5 times 400 meters is 1,000 meter length kind of inside the hill. So imagine if you drilled a tunnel from point A to right underneath point B, it would be 1,000 meter length tunnel. So the adjacent side to the angle of inclination is 1,000 meters. The length up the hill, we could use Pythagorean theorem, and we would take the square root of the one side, which is 1,000 squared, and add it to the length of the other side squared. So the square root of 1,000 squared plus 700 squared is approximately 1,220.66 meters. So if you went straight up the slant of the hill, it would be 1,220.66 meters. Now, the angle you could get by using any of our trig functions. Inverse tangent is probably the most obvious because we have opposite side over adjacent side initially. So if I take inverse tangent of 700 over 1,000, I get 35 degrees. But I could also use sine or cosine. If I use sine, then I would do inverse sine of the opposite side of 700 over the length of the hypotenuse, which is 1,220.66. If I use inverse cosine, then I'm going to use the adjacent side of 1,000 divided by 1,220.66. Inverse sine and inverse cosine of those ratios also give 35 degrees. In another example using right triangles, we have a rock climber who is close to the top of a cliff. He's 175 yards from another point, and he is currently at an angle of elevation of 24 degrees above someone's sight line. The top of the cliff is an angle of elevation of 30 degrees from that same sight line. We're interested in how much farther he has to go to reach the top. The climber is 175 yards from a line of sight. So that is the adjacent side to our two angles of inclination. And the height to the top of the cliff is from an angle of inclination of 30 degrees, and where the climber currently is at an angle of inclination of 24 degrees. So tangent of 30 degrees is going to be the full length from the sight line to the top of the cliff divided by the adjacent side of 175. And then tangent of 24 degrees is going to be how high the climber is from that line of sight over the distance 175. If you multiply both sides by the 175, you can solve for the full length to the top as well as the length to where the climber currently is. 175 times tangent of 30 degrees is 101 yards. 175 times tangent of 24 degrees is 77.915 yards. If I subtract the full length to the top minus the height the climber currently is, 101 minus 77.915 is 23.085 yards left to go. In our other examples, we were using right triangles in the problems, but sometimes you don't have right triangles. And if you don't have a right triangle, you cannot use Pythagorean theorem. You cannot use those definitions of sine, cosine, and tangent that we were using. They assume you have a right triangle. But using right triangles, a couple other laws can be proven that are helpful when you do not have right triangles. One is the law of sines. The law of sines points out that for any triangle, sine of an angle divided by its opposite side gives you the same ratio no matter what angle you pick in the triangle. So it's written as sine of A over length A equals sine of B over length B equals sine of C over length C, where A, B, and C lengths are opposite A, B, and C angles. There's another law called law of cosines, and it starts off like the Pythagorean theorem. A squared is one of the sides. It equals the sum of the squares of the other two sides, but then there's a correction factor. You subtract 2 times the other two sides multiplied times cosine of the angle that was opposite the original side. So notice cosine A, angle A is opposite side A, and side A was all by itself on one side of the equal sign. So A squared equals B squared plus C squared minus the correction factor 2 times B times C times cosine of A. There are some times where one formula is going to be better than the other. There's times where you could use either one. Notice for law of sines, you have to have an angle in between two sides, or you need to have two angles and a side in order to actually solve for the law of sines. And some points to consider. If you're using law of sines, you do have to have enough information for the rule to actually be solved. And so sometimes there's situations in which you want to use law of cosines because you can't use law of sines. For example, if you were only given the lengths of the sides of a triangle, can't use law of sines. If you were only giving angles, you cannot use law of sines. Also, if you're working with law of sines, you should be aware that sometimes you might be given information in which there's actually no possible triangle. Sometimes there's two possible triangles, and sometimes there's one possible triangle. We'll discuss this further in other slides. And when you're using the law of cosines, always start with the largest side. Work with the largest side first. The reason being is that if you don't, you might actually get information when you do inverse cosine that gives you a triangle that you weren't actually given in the first place. One issue that will arise when you're doing these non-right triangle problems is that sometimes you're given a scenario in which there's actually two possible triangles that could be formed with the measurements you're given. Or you could be given measurements in which there's actually no possible triangle, or there's only one possible triangle. I wouldn't really worry about memorizing like situations that give you these. It all comes out in the wash. If you start to do a problem, assume that there might be two triangles and just go with that assumption. If there are no triangles, you're quickly going to realize there's no possible triangle. If there's only one triangle, you'll be able to find the one triangle, and then when you go to find the other triangle, you'll run into a problem. So just be aware that you could be given information that actually forms two triangles, no triangle, or one triangle. And when you start a problem, assume there's going to be two triangles. If there's no triangle or one triangle, you'll hit a roadblock and you'll realize, oh, there's no triangle, or oh, there's only one triangle. We are going to use law of sines to help us figure out how far it is from the city of MUSORE to the city of BAGALKOT in a province of India. We're given information that the distance from Bangalore to BAGALKOT is 260 miles, and the distance from MUSORE to Bangalore is 86 miles. The surveying angle that's at the town of MUSORE is 63 degrees. At the moment, we don't know the other two angles. First, we're going to find the angle that is actually at the town of BAGALKOT. So it's opposite the 86 miles. So we'll use law of sines. We'll take sine of 63 degrees divided by 260, and we'll set it equal to sine of angle BAGALKOT divided by 86. That's using law of sines. If I multiply both sides by 86, then I will solve for sine of angle B, and that is approximately 0.29472. Then doing inverse sine or arc sine of that value gives us a 17.14 degree angle. So the angle at BAGALKOT is 17.14 degrees. I really want to find the distance from MUSORE to BAGALKOT, so I really need the angle that's at Bangalore. But I have a triangle with three angles. I know that every triangle has angles add up to 180. So now I have two of the angles. I can easily find the third by taking 180 and subtracting 63 and subtracting 17.14. That leaves 99.86 degrees as the angle at Bangalore. Now that I have that angle, I can use law of sines one more time to find the distance that I was originally wanting. So sine of the angle at Bangalore, sine of 99.86 degrees divided by the distance I'm looking for, is equal to sine of 63 over 260. Notice the 63 degree angle is opposite the 260 miles. I'm going to do cross multiplying to solve this ratio. You could also flip the two fractions and then multiply by sine of 99.86 degrees. But I'm going to do cross multiplying. So sine of 99.86 degrees times the denominator of 260 will equal sine of 63 degrees times the denominator of d. Solving for d, I'll divide by sine of 63 degrees. And when I type that correctly in my calculator, I get a length of 287.5 miles. In this example, we're trying to find the distance across a lake, and we have some surveying information. We've measured one point that we know is 1.4 miles from where we are, and another point that we know is 2.2 miles from where we are. The angle between those locations from our surveying point is 58 degrees. This is a perfect place for us to use the law of cosines. Notice I cannot use law of sines because I don't have another angle that I would need. And so you would get stuck with having too many variables if you tried to use law of sines. Using law of cosines, we are trying to solve for length d across the lake. So d squared will equal 2.2 squared plus 1.4 squared minus 2 times 2.2 times 1.4 times cosine of 58 degrees. So the 58-degree angle is opposite side D. And then the 2.2 and the 1.4 are the lengths of the other sides. If you carefully type the right-hand side of that equation into your calculator, you get 3.535 miles. That's D squared. D is the square root of that value. So if I take the square root of 3.535, I get a distance of 1.88 miles. In this example, we are looking to find the angles of a triangle formed by connecting the centers of 3 circles. One circle is smaller and has a radius of 4 centimeters. That's the light blue circle. The yellow circle has a radius of 9 centimeters, and then the darker blue circle has a radius of 12 centimeters. If we then connect their centers, we will form a triangle, and we're looking for the angles of that triangle. We will be able to use law of cosines and then eventually law of sines to finish the job. Our triangle has 3 different lengths. The length that's connecting angles A and C is length 9 centimeters plus 4 centimeters, or 13 centimeters. The length connecting C and B is 4 plus 12, or 16 centimeters. And then the length connecting angle A and B is 9 centimeters plus 12 centimeters, or 21 centimeters. When you're using the law of cosines, always start with the biggest angle and biggest side. You'll avoid creating a situation where you potentially might have 2 possible triangles. Here we definitely only have 1 triangle, but if you start with one of the smaller angles, you could kind of create a false situation in which there are 2 triangles and you won't really be able to tell that you chose the wrong one that you don't really have. So always start with the biggest angle and the biggest side. So plugging the values into the law of cosines, length 21 squared is equal to 13 squared plus 16 squared minus 2 times 13 times 16 times cosine of angle C, that is opposite length 21. I'm going to then solve for angle C. So I want to get everything away from cosine of C. So I subtract 13 squared and I subtract 16 squared from 21 squared. That gives me a value of 16. Then I'm going to divide by negative 416. That's multiplying cosine of C. Once I get that value, I want to get C, so I have to do the inverse function. So inverse cosine of 16 divided by negative 416 gives me an angle of approximately 92.2 degrees for angle C. We found angle C in the previous slide to be 92.2 degrees. Now I can use law of sines to find angle A. I could also use law of cosines. There's nothing wrong with using law of cosines. I just thought in this example we could get some practice with both rules. So sine of 92.2 degrees divided by 21 would equal sine of A divided by 16. 16 is opposite angle A. If I multiply both sides by 16, I get sine of A would be approximately 0.7613. I want the angle, so inverse sine of 0.7613 is approximately 49.58 degrees. So we now know angle C, 92.2 degrees, and we know angle A, 49.58 degrees. Then I can just use the fact that all 3 angles have to add up to 180 to get angle B. 180 minus 92.2 minus 49.58 leaves 38.22 degrees for angle B. You could again use law of cosines or use law of sines to get angle B, but we might as well do it the quickest, simplest way. In this problem, we're proposing a scenario in which there's actually 2 possible triangles, and when we use law of sines, we will work to find all the values for both possible triangles. We have a pride of lions that are at a watering hole, and we have a motion detector that's trying to record the movements of the wildlife in this wildlife park. So the lions leave the watering hole, and they leave at an angle of 25 degrees from where the motion detector is. The watering hole was 85 meters from the motion detector. So we've got a length of 85 meters as one side of the triangle and an angle of 25 degrees. The motion detector detects motion in a circle of radius 75 meters. And so the lions get heading towards that circle, and at one point they enter the circle where they get noted, and then they travel through the motion detector's range, and then they eventually leave the motion detector's range. So where the lions first cross through the motion detector range creates one triangle, and when they leave the motion detector range, that creates a second triangle. 25 degrees is opposite one of the radii of the circle that the motion detector makes. So sine of 25 degrees divided by 75 would equal sine of angle C over 85. So 85 was the length between the watering hole and the motion detector, and there's an angle in a triangle that's opposite that. So solving that for sine of C, we get 0.47897 is sine of C. Inverse sine of 0.47897 is 28.62 degrees. So one of the two triangles has a 28.62 degree angle opposite the 85 length. However, sine is the y coordinate as you rotate around the unit circle. So over in quadrant 2, there's another angle that's less than 180 degrees that also has that same sine value. So take 180 and subtract the first answer that you got of 28.62, and you get 180 minus 28.62 is 151.38 degrees. It's possible that there's another triangle that involves the 25 degrees, the 75 length, and the 85 length, and that triangle has 151.38 degrees as its other angle. You can see both of these triangles if you go back to the original screen. Continuing the lion problem, we found that the angle opposite the 85 length in both different triangles was either 28.62 degrees or 151.38 degrees. The 25 degrees was fixed. That was the angle at which the lions left. And then when they crossed into the motion detector range, that created one triangle. And when they leave the motion detector range, it creates a second triangle. So using the fact that all the angles have to add up to 180, I can find the third angle by subtracting 25 and 28.62, and I get 126.38, and I can take 180 minus 25 minus 151.38, and I get a little angle of 3.62 degrees. And then those angles will help us find the other possible lengths. So again, using law of sines, I would have length B divided by sine of 126.38 would have to equal the ratio of the 75 length over its sine of opposite angle of 25 degrees. Notice I've written the law of sines flipped upside down, but that's perfectly fine as long as you flip both fractions. So solving that for B by multiplying by sine of 126.38, I get a length of 142.88 meters. Setting up the same type of ratio with the 3.62 degree angle, I get B is equal to 75 times sine of 3.62 degrees divided by sine of 25, and that gives me an 11.2 meter length. So if you then go to the picture, we can kind of put all of this together. Okay, after our work, we now have the whole situation of what happened with the lions. They left the watering hole at an angle of 25 degrees. They were 85 meters from the motion detector at that point. When they hit the motion detector range, they had gone 11.2 meters, and then they kept going, and when they eventually left, they had gone a total of 142.88 meters. The 3.62 degree angle was the little angle that's opposite their original length when they were first hitting the motion detector, and the 151.38 is the angle that the radius of the motion detector makes with their original line of that they left. And then when they left the motion detector range, the 28.62 degrees is the angle made with their line of path and the other radius of the circle. This picture is not drawn to scale. The scenario was kind of just blocked out and the scale was not paid attention to. So I know the 11.2 meters looks a lot longer than it really should. It should be a lot shorter in relation to the 142.88, but all the measurements are accurate with the numbers that we were given.